the indications sent to me were to address a case study application in smart building. So we are in the range of small size in terms of power, installed power. Then the other indication, the other must is to hybridize at least 2 energy storage technologies. So the boundary condition was that Peter will speak about vanadium redox flow batteries. So the technologies I consider are other 2, so different technologies. Specifically, I will speak you about an hybrid system, energy storage system composed by an energy intensive, so a lithium-ion battery pack, and a power intensive technology, specifically a flywheel. Okay? Okay. So it is a general slide about the flexibility, the additional flexibility that energy storage can provide to the electric system and the energy system to address the clean energy transition, and specifically the hybridization of different energy storage technologies can provide several advantages, such as the increase in cycle efficiency, because each technology can be managed, operated in optimized operating range, and the global performance of the hybrid energy storage system can overcome the performance of the single-based technologies. This is our must, and today I will prove you with reference to our specific application case. So another point, a very interesting point that we will address today is the potential extension of the device's lifespan, specifically with reference to the battery. Okay? So we need a power-intensive technologies, in this case a flywheel, but we can address a similar system, for example, implementing a super cup coupled to a battery. The target is to achieve enhanced performance of the energy storage system, the hybrid energy storage system, and the lifespan extension with reference to the battery pack is a main target, because it has a strong impact on the economic aspects. Okay. Specifically, flywheel. So we are in a residential application. So we have to contain capex. I don't know if you are familiar with flywheel technologies. Flywheel technologies are divided into main families: the low speed and the high speed flywheel. The low speed implements a steel rotor and mechanic bearings, and have a lower cost, while high-speed flywheels implement composite material rotors and have magnetic bearings. So the efficiency are higher since we have not friction losses. Okay, only aerodynamic losses that are in both cases are limited as much as possible, because the flywheel is equipped with a void auxiliary system. Okay. The flywheel technology has a long lifespan, and it is and this very long life is guaranteed also if the flywheel is operated with full discharge, so 100% DOD. Okay, this is the characterization of the profile. So the electrical profile of our application is a multi-user residential profile. The power peak is 29 kilowatt. The mean value in yearly basis is almost 2 kilowatt. And the building is equipped with a photovoltaic plant. The peak power, installed peak power is 11 kilowatt. So in the graph, you can have a typical load profile for a winter day, while in the red profile is a daily profile for a summer load, summer day. Sorry. Okay, the residential profile usually are, if you think to a residential profile, you think to a very smooth profile with two peak, one at the lunchtime, one at dinner time. It is not in this way. These are the data from a British database that measure the load profile for 2 years at 20 apartments, 20 houses. And it is a very oscillating profile. Okay? So combining, the load profile and the PV profile, generation profile, we have a very oscillating profile to be managed. And the idea of our hybrid energy storage system is to have to devote the flywheel to manage the oscillations and to leave the battery to manage a smoother profile. Okay? This is the scheme. I don't know your background. If you are more in the material field or somebody of you more in the engineering field. This is an application case study, so it is more in the engineering field. And if you have any problem on the comprehension, also after my presentation, I can provide you some material papers to have more explanations. So I want also to promise that we will address this case study, the same case study, from several points of views. So first, the extension of the battery lifetime, both from a simulation and experimental point of view. Second, the limitation, the mitigation of the oscillation at the point of common coupling. The point of common coupling is the point of interface with the grid. So we reduce also the stress towards the grid. Okay. Third, we will examine also if it is better to have an AC bus or a DC bus. This is a more electrical point of view, but anyway, we can address also this point. And fourth, we will address also the power management issues. Because if we have in a hybrid system, we have more than one energy storage device, the power management system and the optimization of the power management system according a multi-objective function is of main importance. Okay, so to achieve our targets, the increase in the performance and the increase in the battery lifespan. Okay, this is the summary. All it is based over this scheme. So we have okay, it is not operating. Okay, we have a common bus, in this case a DC bus, direct current bus. At this bus, all the devices are connected. We have the PV array, the battery, the flywheel, and then the residential load. Okay, the point of common coupling is the point of interface with the grid. Okay, we need a bidirectional inverter. This is another point of interest because we need in the future, in particular with hybrid energy storage system, to implement smart inverters. So inverters that in which we can so equipped with an intelligence, so an intelligent algorithm for real-time management optimization. Okay, I don't go more in the technical details. If somebody of you is interested, you can ask me later. Anyway, I provide you also the design feature, technical feature about the flywheel and the battery. So the battery is a 5 kilowatt, 10 kilowatt hour lithium iron phosphate pack operated with DOD of 19%. The flywheel is a mechanical flywheel, so a low cost flywheel because it is a residential application of small size. So the maximum power is 11 kilowatts and the energy content is 2.1 kilowatt hour. So we can also discuss a little bit before to enter more details, the difference in the implement, with respect to the implementation of a super cap. But a flywheel has a more tunable capacity to power ratio. So with so the discharge time can achieve, as in this case, as it is in this case, 15 up to 20 minutes. Okay. So if you need a certain content of energy, so maybe with a flywheel, now there is also, maybe Professor Pasterini can also add something, but we are also in the research for high capacity super cap, but up to now with the flywheel, the margin for the increase the energy content is a little bit greater. Okay. Okay, we can start first with a conventional power management system because we have to manage the flywheel and the battery. In this case, I don't enter now in these three control tree, but if you can see in this graph, you have a red smooth profile and an oscillating black profile. So the idea is to manage the flywheel to address the oscillations and to leave the battery to manage the smoother profile, okay? To reduce the stress towards the battery, on the battery. In this control algorithm, all the technological constraints in terms of power and capacity thresholds are implemented for both the battery and the flywheel according to the sizing features I provided before. So the battery C rate, the battery capacity, the DOD, and the same for the flywheel. For the flywheel is a little bit different because the flywheel is equipped with a reversible electrical machine that can operate both as a generator and a motor. And so we have to consider the characteristic curve of the electrical machine in both operating modes. Okay. This is a simplification of a visualization of how this algorithm works. So the battery is operated over the step profiles, while the flywheel manages the difference between the difference profile, the current, the instantaneous difference between the PV generated power and the load. Okay. We have to manage the difference, the instantaneous difference in power between the PV generation and the load, because we want to limit as much as possible the exchange with the grid. So we want to have ideally a completely independent building, okay? And the second target is to reduce as much as possible the derivative of the power at the battery terminals, okay? To reduce the stress on the battery. So the battery works over this step and the flywheels manage the difference between the power profile to be addressed and the battery power. Okay, all the models, so the entire microgrid, PV array, the battery in the flywheel is implemented the model in Simulink MATLAB environment to have a dynamic model. but we don't. I don't enter now in details and so much details. So what we obtained is an early base power profile. So step by step, we have the power required to the battery. So if it is absorbed or delivered, is the same, okay? And we have this power profile for all the year, okay? We know also which is the state of charge profile of the battery. So now, how can we assess the expected lifetime of the battery? Okay, we will do it both by simulation and experimental activity. First, by simulation, we can move from the simulated state of charge profile required to the battery by applying the rainfall algorithm. The rainfall algorithm doesn't provide an accurate estimation, but is useful to compare different management strategies or different sizing conditions to have a comparative information about the performance and the lifespan related to different operating conditions. So in few words, the rainfall algorithm before moves from the state of charge profile of the battery, identifies the local minimum and maximum, and then identify the fragments of cycles that the battery performs, okay? Then you know for all these fragments of cycle, the DOD, and you can count for each DOD class the number of cycles. Okay, so you obtain the graph on the left, so the cumulative distribution of cycles number versus DOD for the battery. In this case, when it is in the blue profile, when the battery is implemented in the hybrid configuration, and the red profile when the battery is alone. So I consider a battery of equivalent capacity with respect to the hybrid storage system. So the battery capacity is the sum of the capacity of the battery in the flywheel. Okay. Good. If I count all the cycles for per each DOD class, then I can apply the rainflow algorithm that couple the results of the cumulative distribution with the failure cycle to failure curve of the technology. The results is an estimation that's results for the hybrid system in a gain of 3.6. So there is an extension of the life of 3.6 with respect to the one of the battery if implemented alone. Okay, you can understand that in terms of money, so capex for replacement of the battery is a strong advantage. Okay, we proceed also from an experimental path to prove the validity of the results provided by the simulation approach. And in this case, so we move from the the yearly base profile of the state of charge of the battery, and from specifically from the cumulative distribution. So we know that in the hybrid configuration and in the not hybrid configuration, the battery for each DOD class has to perform a certain number of cycles. So we perform, according to this indication, an accelerated aging test. The choice is only to perform each cycle at the maximum discharge power and the maximum charge power. So it is true, we stress a little bit more the battery, but we stress the battery more in both cases. So both for the case of the hybrid system and for the not hybrid system. Okay. And so we performed a test equivalent to 3 years of operation above the battery, the cells. And in the picture on the right, we have with a certain approximation, but the validation of the simulation results. So you have the trend of the percentage increase of the battery internal resistance, and the percentage increase of the internal resistance decreases of 1/3 in the case if the battery is implemented in the hybrid system. Okay? And it is a strong information, in my opinion, a relevant information, because nowadays technicians, hybridization is not in the best practice of technicians before the capex is higher, before we need we need a bidirectional inverter with more ports, so inverters that have to be so with a smart inverter. Okay, so there are complex components, and we have also to develop a proper management strategy. So it is more complicated. Okay, and this is the first result. So we have obviously also a reduction in the exchange with the grid, but I will address this point at the end, because I would like to show you the difference between a conventional power management strategy and a stochastic power management strategy. Okay, so in that case, we will, at the end, we will see also the results to regard to this point. Okay, second point, how the oscillation at the point of interface with the grid are reduced. In these are some for 1 day, for 2 days, the results of the simulation code. And you can see when, for example, you have a cloudy day, the oscillation due to the residential load are more relevant, and the flywheels works more. So on the bottom, we have the graph reporting the flywheel power. Okay, while in the middle we have the profile of the battery state of charge, and in the upper one the difference, the instantaneous difference between the PV generation and the residential load. Okay, we can also manage assess the profile at the point of interface with the grid, and here it is calculated the power ramp, so the difference between two consecutive time step in the power exchanged with the grid. And here on the bottom, you can see also the cumulated distribution of the power ramp. And it is clear that if you go to the 95%, we have a reduction of 4 times in the power ramp. Okay, so in the oscillation that the power has at the point of interface with the grid. Okay, this is a more complicated point. We have a more electrical aspect, and the system is always the same. We can choose also if to have as the common bus a DC bus or an AC bus. Okay. And so in this case, we perform an electrical analysis on the microgrid, considering the different topologies of the microgrid. And these are the models of the two microgrid topologies. We consider also priority load and ordinary load. So the priority loads are the loads that has to, for example, elevators, safety equipment, and other. Okay, and we consider the behavior of the two topologies at the occurrence of sharp variation of the load. For example, the case one is the case in which the load moved from almost 5 kilowatt to 13 kilowatt. So we have we pass from supplying the load exclusively from the PV to use the store energy stored in the hybrid energy storage system. While the case two, we move from a lack of the PV production because consider that the load moved from 9 kilowatt, so is higher than the PV production, to 1 kilowatt 0.5, so it is lower. So in both cases, we have two sharp variation of the load that correspond to the pass to pass from two different modalities of operation of the energy storage system. Okay. What we found from so we analyzed the three-phase current, and we have not difference at the load terminals, but we have difference at the grid interface. And in particular, in the case of the AC bus, we have a reduction 30% of the transient before stable conditions are established. And we have also a lower peak in the current. We analyze also the distortion. So it is a very, very electric technical point, but the distortion, the power quality is it is a very relevant point, and increasing the number of renewable plants, and so the number of converters that are connected to the grid, power quality will become a very, very critical point for the number of harmonics. Okay, harmonics are the cause of faults of electrical, electronic equipments, and so on. And we provide the analysis in terms of the total harmonic distortion in terms of voltage and current, and there is not a relevant difference. Finally, it is evidence that the AC architecture can be integrated on pre-existing power infrastructures. And so it is a more viable, it appears as a more viable solution. Okay. Last point, the optimization and the relevance that the power management strategy can have in the operation of a hybrid energy storage system. In this case, since renewable and also load have renewable generation profiles, and also residential loads have a nice stochastic character, we decided to apply the simultaneous perturbation stochastic approximation algorithm. It is a stochastic algorithm, and the point of strength in the application, it is that it doesn't require a mathematical model of the uncertainty. It has an implicit model of uncertainty. And which is the, in this case, we can determine a multi-objective function, so we can decide which are the targets of our application. We can formulate in a mathematical way our targets, and so we can define the function, the multi-objective function that has to be optimized. in real time, step by step, during the operation of the hybrid energy storage system. This is how the algorithm operates. It is the name is a perturbation stochastic approximation. So we move from a vector of parameters, we perturbate with a gradient the parameters, okay, adding, subtracting the perturbation. We calculate the gradient of the loss function once the parameters are perturbated, and then we have to check the convergent conditions, okay? And the algorithm iterates in this way, but we don't go in details in this. Okay, it is instead of interest the formulation of the problems with respect to our case study. So it is the vector parameters are the split factor of the power. So each instant we have the difference to manage the difference in positive or negative between the PV generation and the load. Okay, and this difference has to be split among the flywheel, the battery, and if it is needed, the grid. Okay, we want to minimize this contribution. Okay, these are the parameters. Then our target, we want to reduce the exchange with the grid. So it is on the right, you have the mathematical formulation of the minimization of the exchange with the grid. Second, we want to extend the battery life. So we want to smooth the power profile at the battery terminals. And on the right, we have the condition from a mathematical point of view of a minimization of the derivative of the battery power. Okay, so we can combine in a single function the two objectives, and we can assign also different weight to the two objectives. Okay, what we found in this case. In this graph, we have the results of the, so we developed this this algorithm. We implement in the dynamic model this algorithm, and we run more simulations. The simulation were run varying the weather condition, so apply some attenuation factor to the PV generation, and moving with different initial state of charge of the battery. Okay, so in this label, when I have a state of charge 50, I have 50% of the initial state of charge of the battery. M equals 0.5 or M equal 1, so it is the attenuation factor. So M1 is the clean sky, 0.5 is a cloudy sky, okay? And we determine for moving from the simulated power at the battery terminals, the power ramp. So second by second, we calculate the oscillation in the power oscillation at the battery terminals, okay? And the graph are the cumulated probability. So I don't know if I think you are familiar with this kind of graph. If I go, for example, 0.5, I can find on the bottom trend, for example, about 6 ampere. It means that for 50 half of the operation time, okay, I have an oscillation current at the battery terminal of 6 ampere. Okay, so all the results related to the stochastic algorithm are on the upper part. So it means that the oscillations are strongly reduced. And we have, when you see on the label A1 is the previous algorithm I showed you before. In the rectangular in the center, we have a zoom. And we can, now it's hard to recognize each label with the trend, but the stochastic algorithm is provide the lowest values of current oscillations, and moreover, it is more robust because the performance doesn't depend on the boundary conditions. So it is less affected by the sky conditions and also by the initial value of the battery state of charge. It means that the power management algorithm is robust. Okay, so the battery is safer with this algorithm with respect to the previous one. Second, in our mathematical formulation, we implemented two targets. One is the extension of the battery lifetime. The second is the minimization of the energy exchanged with the grid. And these are the results. These are the results for only for the clear sky conditions, considering two different value of the initial state of charge of the battery. And on the left, we have the results obtained in the case of the stochastic algorithm. And you can see how the blue sector is smaller on the left column with respect to the right column. Okay? Okay. I finished with my presentation, and we have also results for the same system, also of LCOE, levelized cost of energy results, but I know there is no time to present this, but if you want, I can provide you with hybrid system compared with a single lithium-ion battery installation or vanadium redox flow battery installation. Because with the levelized cost of energy approach, we can assess both CapEx and OpEx, and the replacement is a critical part, is a relevant part, and we can have the evidence of how hybridization can be beneficial also from economic point of view. Okay? No more. Thank you.